let's have a look at some of the key ideas in Level 3 Inference. So overall, the whole idea about inference is we've got a population that we're interested in. Now, we can't often go and do a census of that entire population for two reasons. Often it costs a lot of money and it takes a lot of time. So because of those issues, most companies will actually go and take themselves a sample of data. And what we are going to do is we're going to analyse that sample, okay, and then we're going to use that sample to make an inference about what we expect to be, what we would be able to see in the population as a whole, okay. So first of all, measures of spread. There are three general measures of spread: mean, median, and measure of centre. And what we're looking for is we're looking for where the middle of the data is, okay? So I can say, right, the middle of the data is around about there. And there are three different ways that we can measure it. The mean is when I was add up every single one of these data values, add up all those numbers, and divide by how many numbers I've got. The median, I'd be looking for which is the number in the middle position. So what I would be doing to work that out is I'd be going from one end to the other, matching up and going, right, find the number in the middle. And I would go through one at a time and work my way till I found where that middle is, okay? The other one is the mode, and the mode is the most common number. We don't tend to use it as much when we get to senior levels, but occasionally it's useful. Measures of spread. There are two measures that you need to be aware of. There is our interquartile range and there is the standard deviation. Okay, so what these both are doing is they are looking at how spread out the data is. Now, way back in primary school, you will have done the range. And occasionally, very occasionally, we use that. That's when we're looking at where's the smallest number, where's the biggest number, and what's the difference between it. So how spread out is all the data in between. Now, for year 13, we're not worried about that. The interquartile range is the upper quartile minus the lower quartile. So if I look at the box and whisker graph, it's saying, well, here's my lower quartile, here is my upper quartile, okay, and I want to find out how spread out that middle 50% of the data is. So that's our interquartile range. Standard deviation is a slightly different measure. It's just another way of measuring the spread, but what it does is it fits our data over the top and says, right, the mean or the middle is about there, and it's looking at how much spread there is on either side from the centre. Okay, so those are the different measures of spread we need to be aware of. Shape, we've got a number of different shapes that we need to know. So we've got our lovely hill-shaped one, which is what we call our normal distribution. We've got this one here where we've got a tail, a much longer tail on the left-hand side. So that makes it into a left-skewed distribution. Equally, if you've got a box and whisker, you can look at where the median is and look at the distance from the tails on either side, and you can see that the one on the left is much longer, so the data is more spread out. The next one, we've got a longer tail on that right-hand side, so that is going to be right-skewed data. And same with our box and whisker graph. Find your median and look at the distance to the bottom and the distance to the top, and you'll see it's much more spread out on the right-hand side of the data. The next shape is bimodal, and this is when I've got two different peaks there, okay? So one peak in the middle there, or one peak there, one peak there, two peaks, that's the word for bi. Or the last one there is uniform, and the particular thing that we're looking for here is that the sides are really, really flat. It's not like the normal where our sides go down, our tails go down nicely. For a uniform, the sides are straight up and down, and the top is pretty flat. So here's an example for you. What we want to do when we look for shape is we want to just draw a quick match over the data, look at that, and in this case I would call this a bimodal shape. Okay. What I don't want to see is I don't want to see you doing like this kind of skyscraper approach. Okay. I don't want that. I just want a very quick over the top, what's the general shape. Okay, so that's what those things are. Now we actually need to do some analysis. So when we're doing our analysis, one of the first things we need to do is compare where the centre is. So most of the time we're going to be looking for median, and I'll talk a little bit about when we use mean or median later in the video. Most of the time though we're going to compare the median, and we are looking for where the middle of one group is, where the middle of the second group is, which is not quite at the right place, that's better. And in particular, I want to know which median is bigger, and in this case the male median is bigger, and I want to know how much bigger it is compared to the females. So I can do that graphically, or I can do that using the summary statistics on the side there. And so I can see that the male median, that's at 81.85 kilos, and the median weight of females is 68.45 kilos. So that is a difference of 13.4 kilos. So I can say there in comparison that the median weight of males is 13.4 kilos more than the median weight of the females. All right, so that's explicitly what I'm interested in, and I'm interested in what the difference is. Now, thinking about mean versus median, what I want you to think about is what happens if I've got a normal distribution, for example. And in a normal distribution, the mean and median are both going to be pretty close together in that centre. So both the mean and the median are around about the same place. So in that particular case, I could use either of those. I could use either the mean or the median. And sometimes in that situation, I'm actually going to, if I had to choose, I'd prefer to use the mean because it's a more complicated measure and therefore is slightly better than the median. However, and this is where there's a big but, what happens if I have data, for example, that is right skewed? So my median, which is, remember, a median is just finding the number in the middle position. The median is going to be just to one side for right skewed there, okay? However, the mean, think about what happens when you've got a mean. To find the mean, you've got to add up all the numbers and divide by how many numbers you've got. So if I've got a house worth $10 million and $9 million and $8 million and so on, when I add those massive numbers together, that is going to pull my mean towards that long tail. Okay, so if I've got right skewed data, the mean gets pulled towards the tail. Vice versa as if I had left skewed data, okay, and in that case, my median is just slightly to one side of the mode, and the mean is going to get pulled down in the direction of the tail. So in both of those situations, all right, so in both of these situations here, the mean and median are not going to be at the same position. So one of these measures is better than the other. And in that case, the one that's better is the median, because the median is much more stable. It's a much more stable measure because it's not interested in what the outliers are. It's only interested in where the middle positioned value is. Okay, so we can do all of this analysis with either mean or median. Most of the time we'll do it with median because we don't know what shape data we might get. All right, so that's looking at the centre. Now let's have a look at comparing the spread. So as I said before, we've got two ways we can do this. We can either do that with the interquartile range, or we can do that with our standard deviation. So interquartile range is upper quartile minus lower quartile. And if I was doing that for the females here, then the female median upper quartile is 74.5 kilos, and the lower quartile is 60.7 kilos. So when I subtract those two, I get a value of 13.8 kg. And so that is looking at how spread out the middle 50% of this data set is. I want to compare that to the spread of this middle 50% here. And what I notice when I'm looking for spread, I'm not looking for tiny differences between them. I'm looking for is one maybe double the size or triple the size of another, or are they quite similar? And in this case, I would say that the spread of the males, that interquartile range there is a little bit bigger. So a little more spread out than for the females. So, but I'd also go and calculate the interquartile range for that one by doing the upper quartile of 91.1 minus the lower quartile of 72.9, and that gives us a value of 18.1 kilos, which you can tell is a little bit bigger than the 13.8 kilos. So that's telling me the middle 50% of the females is less spread out than the males, or vice versa. The males is a little more spread out. The middle 50% of the males is a little more spread out than the females. Now, the other thing that I could look at was that standard deviation. So if I look on the side here, we can see there our standard deviation for our females is 10.975, and our standard deviation SD for our males is 12.639. So that again tells me that the spread of the females is smaller than the spread of the males. So they're both giving me the same result. And I'd expect that most of the time, except in the case of this whole, it's like the same idea of mean versus median. If I've got normally distributed data, then they are both good to use. If I've got skewed data, then the interquartile range is a more stable measure to use. Okay, so that's the analysis. Then we get to our conclusion part. So in the conclusion, the key idea about this is the word inference. The word inference means to infer or to suggest. So we're going to use our analysis of our sample to make an inference about what we think is true in the population. Okay? So to do that, we're going to use a process called bootstrapping. Now, there is another video that I've set aside to show you guys on how to do this. So please watch that one to learn about it in more detail. This is just a very quick snapshot of it. So what happens is we start with our population. Okay, that's where I'm starting from. I have some data that I'm interested in. I'm not going to go and do the whole population. I can't go and measure the whole population, so instead I take a sample of size n. Now, once I've got that sample of size n, I go and find its mean or median, and I find the difference between the medians. So I do one median minus the other median. Then the bootstrapping part, and this is what the bootstrapping part here is. What is it going to do? It's going to resample from that sample that we've taken. So I'm going to randomly select values from that sample, and I am going to calculate new medians and the difference between the medians 1,000 times. Okay. So I'm going to go through this resampling process 1,000 times, and that gives me an estimate gives me a confidence interval estimating what the population value might likely to be. So let's have a look at an example of how to do that. So on the top here, I've just got my dot plot of my box and whisker of my males and females, and it's looking at their weights. And remember how when we did that, we found we had a difference of 14.95. So there is that median difference. So this is the difference between the medians. And because it's positive, that tells us that the median of the males is bigger than the median of the females by 14.95 kilos. Alright, so that's what that part of it is doing. And the little hint down the bottom there is it's reminded us which way it's subtracted these two. It's done the male median, take away the female median. Then we've got them resampled, so each dot in this distribution represents another difference between, or another median difference when we resample from the original data. And that gives us this confidence interval that we see. Okay, so the confidence interval that we see here goes from 9.1 up to 19.1. And that's giving us a range of values that we expect the population median to be somewhere between these two numbers. Okay, so that's what we want to be able to interpret, is that this confidence interval is using the sample data to estimate what the population difference between the medians is. Okay, so if I'd taken a sample of 100 boys and 100 girls and weighed them, then I would find that for my sample there's a median difference of 14.95 kilos. However, for what I'm going to estimate is that for all boys and girls, that the median difference between any of them is that the males could be heavier than the girls by between 9.1 kilos and 19.1 kilos. Okay, sampling variability, that's the whole idea here of taking repeated samples. And every time I take another sample, I'm going to get another graph. I'm going to get another set of data. So every time I take a sample, my data is different. Okay, and that's because I'm sampling new people. I've got a new set of weights because I've measured the weight of a different group of people. When I look at what the median is doing, the median moves around a little bit, but it should be in the same region. If I know that the median weight for my sample of boys was 81 kilos, I would expect another sample, maybe 82, maybe 80, 83, but I would expect values around about that same place. Also, if I think now about the conclusion, whether or not there is a difference, have I got enough evidence that there is a difference? And in that case, I would say yes or no. Most of the time, I'm going to expect that to be the same. And just saying that, I realise what I've forgotten to say is back in this one here. When I want to do a conclusion, we can estimate the confidence interval, but in terms of the conclusion itself, is we want to know, do we have enough evidence to say that the median of the boys is likely to be bigger than the median of the girls? And what we're looking for in this case, we're looking at, is 0 inside the confidence interval? Okay, now the reason I'm doing that is I'm subtracting two things. I'm doing male median minus the female median. Okay, say these numbers were the same. So if I had a male median of 80 kilos minus the female median of 80 kilos, that would give me a difference of 0. So that tells me that the median of the females could be exactly the same as the median of the males. And that's why I'm looking for whether 0 is inside the confidence interval. If, however, my male median was 80 and my female median was 60, that would give me a difference of 20. So if I'm getting positive numbers, that tells me that the female median would be bigger than the male median. If it's the other way around, say the male median was 60 and the female median was 80, a difference of negative 20. Because I'm getting a negative answer, that tells me that the second number is smaller. So the first value is smaller and the second value is larger. So in terms of our conclusion, that's our key idea, is 0 inside the confidence interval. And in this case, I can say, well, this confidence interval goes from 9.1 up to 19.1. So 0 is not inside that. So I can say I have enough evidence that the median difference, the difference between the medians no, let me word that differently, that the median weight of males, that's better, median weight of males is larger than the females for all people. And if this data was from New Zealand, it would be all people in New Zealand. Okay. All right, let's jump ahead. If I'm now looking at that sampling variability idea, if I take another sample, what's going to happen? And I now think about the sample size. So here I've got a sample size of 10 versus 100 versus 1,000. And what these blue lines have done, that's doing this lots and lots of times, taking another sample, and the blue lines represent the medians. So you can see with the sample size of 10, that's about that much variation in the medians. And so that's about 15 centimetres difference for each sample that we do. When we get to a sample size of 100, the difference between the medians is the median is a lot less variable. By the time we get to 1,000, we can see there that the median is not moving anywhere near as much. So that means as my sample size gets bigger, the variation is going to get smaller. All right, so that's one of the other key ideas. And that means if I have a confidence interval, the bigger my sample size, the smaller or the narrower the width of that confidence interval will be.